So welcome to a new week in the middle of the pandemic, and again we are in the virtual classroom mode here. Yeah, sorry, but that's life at the moment. So last week, what did we discuss? So last week we discussed some stuff about process management. It was about scheduling, and so we had an overview about different scheduling methods, different scheduling algorithms, preemptive ones and non-preemptive ones, and we had some examples of scheduling in modern operating systems like in Windows and Linux. And last but not least, in regard of process management, we have one big topic left. It's the inter-process communication. And last week we discussed some stuff about different sorts of process interaction. So we found out we have communication and cooperation. Communication means we have an exchange of data, and cooperation means we have shared usage or parallel usage of shared resources. And if we have a situation where several processes need to interact with each other, need to work with each other, we also have the timing factor, we have the synchronization factor. So because the operating system or the developer need to decide which actions are done first, what is done next. Do we have an order at all, or doesn't it even matter? And we found out synchronization is the most elementary form of inter-process communication. So we started with synchronization of processes, and we started with signaling. Signaling says one process tells another process that he may continue, that he may execute the operations in its critical section. You remember, critical sections are sections in processes, areas in processes where we have operations where common data is not only read, it's also modified. So we have write operations in critical sections. And if we don't handle these critical sections well, we may have race conditions. Race conditions, you have seen last week, will lead to bad consequences often. So we started with signaling. Signaling was pretty straightforward. One process tells the other, okay, you may go or you need to stop. And we discussed two different ways of how to implement this. We discussed active waiting, the spin lock, which is pretty bad because it wastes resources, and we have passive waiting. Passive waiting is much better. And so yeah, signaling was pretty simple, and it has one strong limitation, one strong drawback maybe. We can only specify here an execution order, but sometimes we don't even care about the execution order. We just want to prevent any overlap situation. Yeah, we just want to prevent race conditions, and we don't care about the execution order. So In this case, we have the so-called locking or blocking method, which can be used for inter-process communication. So we have two functions here. We have the lock and the unlock. Both are executed on a locking variable here. It's called S here. And obviously it's also pretty simple functions. So in unlock, we just have a reset operation. So if the lock or signal variable, you may call it here as you want, if the variable is locked, if it's set, so it's reset, and in unlock, the process also checks, do we have any waiting processes, do we have a waiting process, and if yes, it's deblocked, and if not, we just continue. And the lock operation here, it checks if we have the signal variable, if we have the variable as set, and if yes, the process blocks itself, and if no, it may continue. So here in our picture here, in our image, we have a very simple example. We have two processes with two critical sections, and they are protected from overlapping execution, from parallel execution by lock and unlock. If you want to implement something like this, it's not so difficult. You have several options here in Unix operating systems. You have several system calls present, and also standard library functions of the same names, which can be used to implement the functionality of lock and unlock. Some examples here are signal suspend or kill, pause or sleep, and two signals here which can be used. Here we have one alternative mentioned. You may use the signals signal stop and signal continue. They have the numbers 19 and 18, and you can send them to processes by using the command line tool kill, with kill 18 and the PID, and kill 19 and the PID. You can do this, and so you can stop and reactivate processes. Another alternative, if you want to implement something like this, it's also pretty straightforward. You may just use a local file, a file in one of your local file systems, and so it can be used as a locking mechanism for this mutual exclusion issue. So for this alternative scenario, just each process needs to verify before it enters the critical section if it can open the file exclusively. This can be done by the system calls open or the standard library function fopen, and if it's possible, everything is fine. If not, the process needs to wait, and so we can do this wait operation or wait scenario in different ways. So maybe by the system call sleep, if we want to do busy waiting, or by using sleep or pause and waiting to be woken up by another process at some time, so just by implementing a passive waiting scenario. Yeah, that's two alternatives which are not so difficult to implement. So we have some hands-on ideas of how to implement things like locking and unlocking. So yeah, time for a summary. What were the differences between signaling and blocking? And that's truly something you should try to remember. So in signaling, as mentioned before, we specify the execution order, and in blocking, and when using blocking or locking, we just secure critical sections and we do not specify the execution order. We just prevent any overlapping situation of critical sections. If we use something like blocking or locking, and we just tell processes they need to wait for some time, we also may run into trouble. That's clear. And two problems can arise from blocking processes. One trouble is starvation, which means a process never removes our lock, and so other processes need to wait infinitely. So they are not dead, but they cannot continue to work. So they wait infinitely long for the release. And the other situation which may happen is a deadlock situation. Deadlock is quite well known, I think. So a deadlock situation means we have several processes waiting for resources which are locked by each other, and the processes are locked each other, have locked each other mutually. Yeah, that's a pretty bad situation, and here I have some pictures explaining it quite well. The left one is maybe it's a bit heartwarming if you have lived in Mannheim for some time, or if you know the city, so maybe you remember the city map now of the city center in Mannheim. The right picture here, it's not from mine. I found it in the internet, and I have no idea about the author or source, but it's a pretty bad deadlock situation shown. And when we talk about processes in operating systems, it's pretty similar. The interesting thing about deadlocks is it's quite old. The topic of deadlock management or handling processes, so to prevent deadlocks, that's a pretty old topic. And more than 5 decades ago, some people found out and published about their outcomes in deadlock occurrence, and so they found out that a deadlock situation can only happen if four conditions are fulfilled, and they need to be fulfilled all the time. So if just one is missing, we will not have a deadlock situation. These people called Kaufman and so on, they had an interesting publication here, System Deadlocks called, from 1971, and the conditions they identified, it's the mutual exclusion. So we have situations that at least one resource is occupied by one process, or it's available, so it cannot be shared. Next condition is hold and wait, which means processes that already have resources may request further resources which are occupied by other processes. We have no preemption, which means the deallocation of resources that are occupied by processes, it cannot be done by force, so the processes can only give them back on a voluntary basis. And we have the circular wait, which means we have a chain of processes which wait. Processes that have resources wait for other resources that are occupied by other processes that wait for resources which are also occupied, and so on. Yeah, as mentioned before, we just need one of these conditions to not be fulfilled, and so we get rid of deadlocks. But if they all exist, we may run into trouble. And when we talk about deadlock detection or prevention, there are two ways in literature quite popular of how to visualize deadlocks or how to calculate deadlocks. And one of these ways is the resource graphs. So we can visualize pretty simple, in a pretty simple way, the relations of processes and resources. And so obviously here, as shown on this slide, we just show processes as circles, and the resources are the arrows between the circles, the rectangles, and the arrows are the edges, or let's call them edges, the edges from a process to a resource. It means the process is blocked because it waits for this resource, and an edge from a resource to a process means the process already occupies this resource. And so it's pretty simple to visualize these relations, and so deadlocks also can be visualized or detected. In my course material, I don't discuss resource graphs as deadlock detection method, not very much, only this slide here, because resource graphs have one strong drawback. Yeah? You can only handle single resources, yeah, not groups of resources. If you want to learn more about this, there's one book which highlights this resource graph handling of deadlocks pretty well and covers it a lot. It's the book here of Baumgarten and Siegert from Oldenburg, publisher. But personally, I don't prefer this method a lot. Don't prefer it a lot, and so that's good for now. There's another method I prefer more because it has a lot more flexibility, and yeah, maybe you will decide for yourself what you like most. So it's the deadlock detection with matrices. So yeah, as mentioned before, with the resource graphs here, we cannot represent groups of resources, only single resources. But if we have maybe multiple instances of a resource, like maybe multiple GPUs or multiple printers or multiple storage devices or whatever sort of resource you want to think about here, you need to use some matrix based deadlock detection. Yeah, this matrix based approach, it uses two vectors and two matrices actually, and the two vectors, it's the existing resource vector and the available resource vector. So the first one, the existing resource vector, it will tell us how many resources do we actually have per resource class, how many resources do exist. The second vector, it will tell us about the number of free resources of every class. So here in the first vector we get to know how many resources do exist, and in the second one we understand how many resources are available now at this moment in time. So next we have two matrices. One is the current allocation matrix, so it will tell us which processes occupy which resources and how many of them at this moment in time. And the final matrix, it's the request matrix, so it will indicate how many resources does every process now need in order to continue to work. Or yeah, maybe that's the wrong explanation. How many resources are required now to allow every process to be successfully executed. Yeah. What is still required? So best way to explain this algorithm is by example, and this example here I stole it. Yeah. I stole it from Mr. Tannenbaum, from his very good book, and so you can be sure it's correct. I just explain it a little bit more extensively. So first, we already got the existing resource vector. The existing resource vector tell us here we have 4 resources of resource class 1, 2 of resource class 2, 3 of resource class 3, and 1 of resource class 4. So next we have the current allocation matrix, and the current allocation matrix is also given, and it tells us which resources are occupied by the processes. Every line in the current allocation matrix, every line is a process, yeah? And or every row is a process, and every column is a resource class, the same as we had here in the vector. So obviously the first process, first row, it has one resource of resource class 3 occupied now. The second process has 2 resources of the second resource, 2 resources of the first resource class occupied, and the final, and here we have 1 resource of resource class 4 occupied, and process 3 has just 1 resource of resource class 2 occupied. So here we have a question: what is a resource class? A resource class can be maybe the group of graphics processors in your machine, or memory storage areas, or printers, or whatever, drives, or any sort of resource which is critical, and you want to find out, do we have some trouble here? Because we have shared resource use, we have parallel process execution, and the processes want to execute such resources. So okay, we learned the existing resource vector is given, the current allocation matrix is given, and finally here what is given next is the request matrix. Request matrix tells us how many resources do the 3 processes here still need to be executed successfully. What is still missing, in other words. And again, every row, every line, every row is a process, and every column is one of the 4 resource classes or resource categories the same ones as we had in the vector and in this matrix here. So, and obviously every process, every one of the three processes still needs some resources to finish execution. Our task now is to calculate the available resource vector. Available resource vector says how many resources do we now have available. And it's basically we sum up the columns of the current allocation matrix and subtract these values from the positions in the existing resource vector, and so we get the answer what is now still available. Okay, so existing resource vector 4 minus 2 occupied here is 2. 2 are still present, 2 resources of group 1, of class 1. 2 minus 1 means we have 1 resource of this category or class left. 3 minus 1 minus 2 is 0. 1 minus 1 is 0. So we have just 2 resources of class 1 available now and 1 resource of class 2 available now. And the resource classes 3 and 4 are entirely occupied. We have no resources present or available anymore now. So now we need to find out, do we have at least one process that can run now? Do we have at least one process that can continue to run, successfully execute by satisfying its resource demands? Okay, process 1, no, because process 1 also requires one resource of class 4, and we do not have this available now. Process 2 also cannot continue to run because this process demands 1 resource of class 3, and we don't have this available now. And process 3, that's okay. The resources it requires to continue to run and to terminate successfully, it's available now. And so process 3 can get these resources, can continue to run, and next it terminates. And when it terminates, the resources which were occupied by process 3, they are freed, they are deallocated. Okay, so if process 3 finishes execution, the resources are deallocated, and now we have a new available resource vector, which is the old one, the old available resource vector, plus the resources which were occupied by process 3. So it's 2 plus 0 is 2, 1 plus 1 is 2, 0 plus 2 is 2, and 0 plus 0 is still 0. So the new available resource vector now is this one. And our request matrix is the same, but process 3 is gone because it has terminated. So simple question, can we allow at least one of these 2 processes to continue to run with the resources we have available? And the first process, no, it cannot successfully continue to run because it still needs 1 resource of category 4 or class 4, and we don't have this available now. Process 2 looks better. It just requires one resource of category 1 and one of resource category 3, and that's fine. So we have this available, and so process 2 can get these resources, can continue to run, will terminate, and will free its occupied resources, which were these ones, 2 and here 1. And this is added to the available resource vector again. And so the new available resource vector is 4, 2, 2, 1. And if we check the new request matrix, yeah, process 2 and 3 are gone. Process 1 is the only one missing, only one left. Can we satisfy these demands? Yes, we can. And so we have no deadlock situation. Yeah? All processes were able to finish operation successfully, and we had no deadlock situation. If you check the exercise sheet 9 and the old exams on my webpage, you will find several examples for deadlock, or several questions for deadlock detection with matrices. It's a wonderful exam question, very easy to correct, very nice for a professor, and also very fair, yeah, because it can be practiced quite simple by the students, and if you understand it, it's really simple in an exam. Yeah, that's it. That's deadlock detection with matrices. As mentioned before, I like it more than the graph-based approach, because it's just more flexible and yeah, also not so difficult, I think. Yeah, some final words about deadlocks. Funny thing, sometimes in computer science we are aware of deadlocks that can happen, but we just accept it, because preventing deadlocks is not always the best idea. Yeah, sometimes people tend to say just live with it, yeah, because if you operate maybe a workstation and it's fine for you to live with a potential deadlock that just happens maybe every few years, but if you want to prevent it, you would waste maybe 10% of your system performance. You would probably say, okay, I live with it. Sometimes it would be horribly complicated to prevent deadlocks or cause some drawbacks. Here we have on this slide just two examples. Yeah, maybe a full process table. Yeah, it's if all your processes are bad, yeah, because they are not running quite nice. Yes, they need to wait for resources, but your process table is already filled, so you cannot start any more new processes, and so this can be considered as a deadlock situation. Or think about the inode topic when we talked about file systems, and I told you the address range of inodes is limited for sure, and if you create many files, you can do so by a loop. You may run out of inodes, and so if you are running out of inodes, you cannot create any more new files, which is also pretty stupid. Such things happen, not often, but they can happen, and they happened before, and they will happen again. But preventing it would be difficult, yeah, maybe by limiting the number of open files, or by limiting the number of created files per user and so on, which is also not very popular. So that's it with synchronization. Yes, that's it. What you needed to learn here in this operating system course about process synchronization. Yeah, and I told you it's the fundament of inter-process communication. Yeah. Before we continue with communication, do you have some questions about synchronization or anything else what we have discussed in the last weeks, months?
I have a question about
Yes.
the process interaction at the beginning of the lesson. You were talking about a value S, and I'm actually not here synchronization exactly. I'm actually not understanding which kind of value it could be. It's just like a signal that the process is sending to another one, and if received, it's just like it's not a value that show if the process is blocked or not. But I don't understand actually which kind of value is it.
Yeah, it's basically a signal you send. Yeah, you can do so by sending a signal via the kill command line tool. But it's definitely not a variable in the virtual memory or in the program code. No, it's by sending a signal, and or maybe by creating some outside resources or so, maybe by creating a file or so and using this as a way of signaling something.
Can I imagine just like a Boolean that is saying yes or no, or?
Yeah, definitely, but it's a Boolean outside of the own memory range. Yeah, it's by sending something out or by executing an operation which results in maybe a file created, which is used as okay, this is used to signal something. Maybe it helps you to understand. Sometimes in daily life, in Unix administration, it's quite popular to create empty files to tell something, yeah, as a log signal, to log something, or to tell a software daemon to tell something. Maybe one example: if you install a new Raspberry Pi with the operating system Raspberry OS, former called Raspbian, it has no SSH server enabled per default. But if you create an empty file or any file in a specific directory which is called SSH, just an empty file with this name, so during boot up, the SSH daemon will understand, oh, I need to be enabled. Yeah, the administrator wants me to run. And so it's basically similar. Yeah, it's something like a signal, but you also can send signals via sending them in the operating system. With kill is a very popular command line tool. You can send signals. Maybe if you want to terminate a process, you can send a kill signal, or if you want to stop it, wait for it, resume it. And so we have different kill signals in Unix-like operating systems.
Okay, that doesn't mean that basically if I'm working with one CPU core, I can only set one S, just like one process that's able to have this variable on.
No, that does not mean it. Yeah, no, definitely not. No. You can have many processes with even with single CPU systems and which interact with each other, and no, that's not
Okay.
You have a lot of flexibility here. in your question, or your question tells me that you need to play around with it's your homework now to play more around with Unix-like operating systems. Trust me, you will get more a better understanding of such things if you do so. Play around with maybe a Linux virtual machine, or even if I don't know if you have a Mac or so, maybe it works the same. You can send signals to process IDs pretty easily with kill. Kill just not always means you kill a process. Yeah, it can also mean you set it to sleep or wake it up, and so you have many different ways of process interactions there. Just play around with it a bit, and the practical exercises on the exercise sheets are maybe a good first start here. So okay, we have another question here. Can you please explain the deadlock process again? Definitely not, because it costs 15 minutes or so, and your fellow student colleagues will start to sleep if I explain everything again now. But I record this session and I will put it online at the end, and so you can watch it over and over again. And if you even have more questions, you can ask me in the exercise sessions, and so I will be happy to assist you in personal. So, any more questions about synchronization? No, obviously not. So let's continue with communication. And yeah, some of you already get a clue. We will not finish this slide set today, and already I did not expect this, because inter-process communication is pretty big. Yeah, it's a very important topic, and honestly one of the topics I like most, because it's most close to practice. Yeah, you will learn here some communication and cooperation techniques which are absolutely close to practice. Yeah, so you can use them in software development instantly. So yeah, communication. So in communication, we have an exchange of data, and this can be done by different ways: by shared memory, by message queues, by pipes, or by sockets. Sockets are the most modern way of inter-process communication. I'm absolutely sure you will learn about sockets in the computer networks course this year. I'm not giving the computer networks course, but I'm sure my colleagues will tell you some stuff about sockets this semester too. So yeah, let's start with first things first. Shared memory. Shared memory is pretty old. I'm not sure, but I think it's the oldest sort of inter-process communication. You have learned a lot about memory address ranges. Yeah, we talked about different sorts of memory management, and we had the virtual memory, and every process has its own memory address range, and so on and so on. And when we use shared memory, we implement so-called shared memory segments, and these memory areas, they are accessible for multiple processes. That's something special, because you remember, in virtual memory, every process is only permitted to operate in its own virtual memory address range. Yeah. So shared memory violates this limitation, or this law, basically. Yeah, if we attach a memory address range to several processes at the same time, we need to make sure that write operations are not executed in this memory address range at the same time. Yeah, it need to be mutually exclusive memory requests here. We as developers need to take care about this. The operating system will not. We need to make sure that a receiver process maybe cannot read data from a shared memory segment before the sender process has finished the write operation. Otherwise we read garbage data, yeah, or we have missing data or so. And if write operations are not coordinated in a smart way, so we have inconsistent data, or we have override situations or so. So it's stupid in any way, and we need to handle this. Yeah, in shared memory we need to be careful, especially careful, and it's the only sort of inter-process communication where the developers need to take care about these things. In all other sorts of inter-process communications, the operating system will handle the synchronization of the read and write operations. So yeah, in Unix or Unix-like operating systems like Linux, it's state of the art that the operating system kernel implements a shared memory table, and here the operating system will manage the information, will store the information about the existing shared memory segments. Here we have some relevant information like size and ownership, privileges, and so on. And so yeah, here we have an overview in this image of how these things, how these components we discussed in the last weeks and months, how it plays together. You remember the memory management unit, a component of the CPU, which is used to map the physical addresses with virtual addresses, and shared memory segments need to start somewhere, so they have also an address range, definitely, and these address ranges are attached to the address space of processes, and so it's just virtual addresses, definitely, and they are mapped to physical memory addresses by the MMU. The addressing is always done by the index number in the shared memory table, and one thing which is still important to understand, in the different sorts of inter-process communication, in these different ways of communication, we cannot always be sure that data is kept by the operating system all the time. And in when we use shared memory segments, as long as the operating system runs, the segments are not erased automatically, so they are kept. If we have a reboot situation, the shared memory segments are gone, definitely, but as long as the operating system instance is present, the shared memory segments are present too. For sure you can erase them by hand, but if you don't do, they are kept. So yeah, how can you play around with it? How can you create your own shared memory segments now? Pretty simple. And to make it a bit more complicated, you have two different ways of doing this. Which one is better? I don't know. depends who you ask. The first way is the so-called System 5 way of implementing shared memory segments and working with them, and the other way is the so-called POSIX API, or the POSIX shared memory segments. System 5 and POSIX are both APIs implemented by the kernel and the operating system itself, and don't ask me what is better. System 5 is definitely older. Some people call it a little bit ugly. POSIX is younger and it's considered a little bit more modern. It has some more features and it's a bit more portable. It's a lot more portable. Personally, I prefer System 5. I don't know why. Maybe I'm more old school or so. Whoa. Who is drawing here with shit? Don't do this. I forgot to prevent this. But whoa! No, you destroyed this. Can you erase it again? Oh no. Thank you. So yeah, I personally I prefer the System 5 thing more. Yeah, in System 5 we have a set of system calls here. It's just 4 system calls, and we have in POSIX we have a lot more. The system calls of System 5 here, it's just shared memory get, shared memory attach, shared memory detach, and shared memory control. And as the names already indicate, in shared memory get, with shared memory get we create segments or get access to existing ones. With attach and detach we attach and detach the segments, and with shared memory control we can modify them or get rid of them or get some information about them. If you want to learn about the shared memory segments on your system, you have one handy command line tool present in your system, at least. It's IPCS. And this IPCS tool here, it will give you a list about the existing shared memory segments. If you want to play around with these system calls, pretty simple. You can just check my webpage and you will find examples there about how to implement the life cycle of a shared memory segment: creation, attachment, detachment, erasing it, and so on. With System 5, and also I have an example about the POSIX API. In POSIX it's a bit more complicated, but yeah, nevertheless some people still prefer it and it's okay. Interesting thing with the POSIX API, if you create POSIX shared memory segments, you can look at them, you can see them, and you can do so if you check the folder device, and here you will find a subfolder shared memory, and here in device shared memory folder you will see files, you will see representations of the POSIX shared memory segments on your system. With System 5 segments that's not possible. Yeah, they are implemented by the kernel, and they are not represented as files. So the programming, my C programming examples about inter-process communication are sadly too long for copying them to single slides. So I need to split this. I want to show you at least the life cycle of a shared memory segment in C, and so I split it. And here we start with the header of the C source code. We have some includes here, a shared memory library and interprocess communication, standard I/O, and so here we have a constant. We specify the constant mem size, max mem size, 20 bytes. Obviously, we have our main function, and we specify some integer variables, one for the ID of our shared memory segment, and one which will hold the return value of shared memory get of this system call. Definitely, obviously, we will use the standard library functions, but the standard library functions will be translated to the system calls of the same name, and so it's more close to practice if we do it this way. And it doesn't matter now if I call it all the time system call or standard library call. So yeah, here in line 13 it gets interesting. Yeah, return code shared memory get. This variable will store the return value of the shared memory get function, and we specify the variable where the ID was specified. We specify the maximum size of the segment, and we specify here the operation we want to carry out. We want to create the shared memory segment, and here we also specify the privileges, access privileges, and in detail it says the user, the guy who owns this segment, who creates it now, it will have, this person or this user account will have write and read privileges on this new resource, on this new segment, and all other people in the same group or all other people which do not belong to the same user group, they will have no privileges at all. So by analyzing the return value, the return code, we can learn, did it work? And if the return value of shared memory get is less than 0, it did not work for whatever reason. Maybe the user had no privileges to create shared memory segments, or there were no resources anymore available, or whatever. But usually it will work, and so we will just get a success message printed out. If we monitor this by using the IPCS command line tool, we will find out a shared memory segment has been created with this key, with this shared memory ID, by this owner, that's myself, with this permissions, and with this size, 20 bytes. So that's what we specified here. And the key, that's what we specified in the source code, but it's shown here in hexadecimal notation. We can convert this on command line just to prove it's correct. We can do this here with the printf command, and so we get the decimal representation of this value, and that's 1, 2, 3, 4, 5, what we specified here. This shared memory ID, it cannot be modified by hand, and it cannot be specified by the programmers. It's provided, it's given by the operating system kernel automatically, and we cannot influence this. So okay, now we created a segment. Now we want to do something with it, yeah. And because a single slide has not infinitely much lines, does not offer so much space. So here I got rid of the error handling, yeah, of this if sequence here. We just here create our segment and we just expect it will work. What do we have further? Additionally, now here we have a pointer specified, yeah, and a character variable for our pointer. Now we want to attach the segment to an existing process, and yeah, we create the segment and now we want to attach it to our running process. Oh, sorry. So here we are. We execute shared memory attach and we specify which segment, the one which is identified by the return value of shared memory get. And don't ask me what these parameters were. I don't remember and I don't care. Yeah, it's obviously it was not so relevant. But if it works, yeah, we will learn by analyzing the pointer and by monitoring this. So if the pointer here is negative, so it did not work for whatever reason, and otherwise it did work. And so here in IPCS we have a modification in the output now. If we compare it with last time, this column here, it is modified, yeah, number of attached processes. Initially it was 0 and now it's value 1 because one process has this segment now attached. Okay, that's also pretty straightforward. So what can we do next? We created a segment, we attached it, and now we want to work with it. And work with it means, in a useful way, we want to write some data into it and we want to read some data from it. So again, we modified the source code a little bit. We still have the shared memory get to create the segment. We still have the shared memory attach to attach the segment. And next, now here in line 20, we try to write some data. It's just a hello world example. We just want to write this string into our shared memory segment, and we identify it by the pointer, which is the return value of shared memory attached. So again, the return value of our operation here of sprintf, it will tell us did it work. If return value is less than 0, it did not work, it did fail. And if it's something else, it's the number of characters we did write. And so we can just execute here a success message and we can inform about the number of characters we did copy into the shared memory segment. Next here in line 20, we try to read the string out of the shared memory segment with printf, and again, if it works pretty well, if not, we get an error message. So yeah, what is missing now? We created a segment, we attached it to our process, we copied some data into it, we did read some data from it, and now we want to get rid of it. And for getting rid of it, we are good programmers, yeah, we do detach it first. So Here again we have our source code a little bit modified. We still have the get, we still have the attach, but we have no read write now mentioned here because that's not relevant now here. We just want to detach it. Yeah. So we have a new integer variable here specified for the shared memory detach operation, for the detach standard library call, function call, or and so here we execute it in line 22, shared memory detach. The segment is identified by the pointer, which was the return value of shared memory attach, and if the return code of shared memory detach is negative, it did fail, and if not, it worked and the segment is detached, and now we want to erase it last but not least. And so here we see we need shared memory control, and shared memory control is a bit similar to shared memory get, because also here we specify an operation, and the operation we want to carry out now is IPC remove ID, so removes this interprocess communication resource, and we identify the segment by the return code of shared memory get. So here we created the segment and here we erase it. Yeah, if it's negative, it did not work, the return value of shared memory control, and else it did work. That's it. That's the life cycle of a shared memory segment. Honestly, it's not so close to practice now because it's just one single process now working with it. If you want to be close to practice, you need to play around with many processes. Yeah, you can create at least one child process with fork, and maybe the parent process writes some data into the child into the segment, and the child process reads data from the segment. But I wanted to keep it here as simple as possible, and so it's just a one single process talking with itself. But it shows well how to work with shared memory segments. Yeah, that's our first inter-process communication way, the shared memory segments. The second one is, maybe you found out, I have no example here about POSIX. Yeah, in POSIX it's not so far away. It's just different functions. If you want to see an example about the POSIX API, I have an example on the webpage of with the course material. It's also just the life cycle of a segment, and yeah, but for reasons of time, and so I will not discuss it here. Yeah, let's jump to the second sort of inter-process communication, and that's message queues. Yeah, message queues, it's pretty also pretty old, maybe same or equal old or close to equal old as shared memory segments, I don't know. Message queues are some sort of linked lists of messages, and it implements the FIFO, first in, first out principle, and so consequently it's often called just FIFO. So processes can store data, can store messages inside these queues and pick messages from the queues, removes them from the queues, and it's the same as with shared memory segments. The queues are not erased automatically by the operating system. So as long as the operating system runs, the message queues are still there, except if you want to get rid of them by hand. So, oh, we have a question. Does System 5 and POSIX automatically handle exclusive write for us to avoid race conditions? No, it does not. In shared memory usage, you always need to handle it by yourself. And next question, how can it be done? This will be discussed in the cooperation part of the slide set. Yeah, we have one tool around, one method around here, which is state of the art, and that's the semaphores. Semaphores are most popular to handle this. Okay, back to the message queue. So we again have some system calls or function library calls of the same name here available, implemented by the operating system kernel. It's pretty similar to shared memory. It's message get, message send, message receive, and message control. I will not explain what these names mean now, because you already know. It's pretty straightforward. And again, we have the tool OPSYS, which is used to monitor and to learn about what goes on in your operating system instance. And again, I have some source code. I think it's really important to get in touch with some C source code here, and to get a feeling of how to work with these technologies. So again, we have here first the header, and we have some libraries included. Again, standard library, standard IO, message queue library, OPSYS library, and so on. And in the main function, we again specify an integer variable. Things are done all the time like this. Here for the return code of message get, because first we want to create a message queue. So we execute in line 13 message get, and again we specify an ID, and now the ID is not outsourced into a variable. Now we just mention it here directly, and we specify an operation, IPC create. We want to create the resource, and again we specify the access privileges. It's the same privileges the user, the owner, will have read and write access. So if the return value is less than 0, everything went wrong for whatever reasons, yeah, and if not, it worked probably, and the message queue we wanted to create should exist now, and it has the ID which is stored in the return code of message get. So OPSYS again tells us what we did, and we created the message queue with this key. The key is again the ID we specified here in the source code in line 13, but it's in hexadecimal notation. If we convert it into decimal notation, obviously it's correct. And the message queue ID here in the second column, that's what is specified by the operating system kernel automatically. We cannot influence this. Here we have the user account, who did it, the owner, we have the permissions again, and we have the number of used bytes and the number of messages stored, and so we have nothing inside yet. So next we need a message to be stored inside, otherwise it's boring. And what do we need? We need a template for a buffer, because the the functions or system calls message send and message receive. They need a buffer to interact with, and in this buffer here we specify a message type and the message itself. Yeah. By using a message type, we can organize messages. Yeah, message type is just a number, and so we can identify single messages. Maybe we have different sorts of messages and handles them with different message types, or maybe we have many processes storing messages in a message queue, and we can identify the sender by different message types, and so we can organize working with the messages. So in our main function we still have the message get in line 17. Yeah, so here we create our queue. The error handling we ignore now, and here in line 20 we specify a message type. Yeah, message type just one now, to keep it simple. And here we copy a string into the send buffer in our buffer template. We just have a hello world like example here. We copy this string into the buffer, and now we can send in line 24 with the standard library function message send and the system call of the same name. Consequently, we can send the message into the message queue, which is identified by the return code of message get. And here we indicate which buffer do we want to use. The one we specified here with these values, and we also need to indicate the length of the message, and here we can calculate this automatically with string length, and the string length executed on this string here. And so if the return value is -0, -1, it did not work, otherwise it worked. And we can prove this. Yeah, we can prove it by monitoring with IPCS, and we can prove it by reading out the message again. So first we prove it by IPCS. Yeah, IPCS will tell us, okay, our message queue, it was empty, and if we execute the message send operation, we will learn, okay, one message is now inside and it has a size of 80 bytes. 80 bytes, that's what we specified here. Obviously many bytes non-used because our message was not so long, but okay, we don't care now. Okay, so we store the message in the message queue, and now we want to pick it out. Yeah, we want to read it from the message queue, and we do this by message receive. So again, we have our example. Not much has changed as first sight, first glimpse. So we have our main function. We do not just have the message get return code variable specified here. We also have the return code message receive variable specified here. And sorry, we create our message queue again in line 17. We have no error handling, why we don't care now. And now we want to read our message from the queue. Because the queue already exists, we open it, and our message was inside. Yeah, it is definitely inside. We wrote it into it formally, and we specify the message type 1, which already indicates we want the first message of this message type to be picked, and here we execute message receive. And message receive, it will read, it will pick the first message from this queue and will use this buffer, and the size here 80, and it will pick the first message of this type 1. If the message is too long, we will just truncate it, and we don't want any blocking operation of this function. We will just continue if nothing is inside which matches, so we don't want to wait. Yeah, we just accept it. So if the return code is it's less than 0, it did not work, maybe because nothing was inside or so, and otherwise we will pick the message and we will print out what was inside, and yeah, we also learn about the number of characters, because that's the return code of message receive. Yeah, and finally we want to get rid of it to complete the life cycle. We want to erase it, and that's done with message control. So again, here we create the message queue with message get, and we erase it with message control. That's really similar to shared memory control. Some slides before, we specify the resource by the return code of the get operation. We specify what we want to do. We want to remove the resource, and so the return code will tell us did it work or not. So that's it. That's the life cycle of message queues in System 5. In POSIX it's not so much different. Again, it's just different function names, and it has some more flexibility, POSIX, because in POSIX you do not just have a standard blocking write operation. You also have a timed send operation, so you can specify a timeout if you want. You have different sorts of receive operation also in a blocking sort or with a timeout sort, and so you have just some more features here. Interesting thing, if you want to watch, if you want to monitor the message queues, you can again do so if you check the folder message queue in devices, and so every message queue here, every POSIX message queue is represented as a file entry, and you can check the content. Pretty simple. So if you want to play around with this, again, here we have an example on the course web page, and so I think that's good for here now. Don't ask me what is better. Personally, I like the System 5 way to go a little bit better, but I think probably because I learned it as a student, and so I'm more familiar with it. But other people hate System 5 and always go the POSIX way, and it's also fine. Yeah, last but not least, we have pipes. No, not last but not least. Third option, third method to go. It's the pipes. Pipes are a pretty simple, very simple way of inter-process communication. It's just communication channels between two processes, buffered communication channels. And we have two different sorts of pipes, the anonymous pipes and the named pipes. And if I check the time, we have 4 minutes left, and honestly, I think synchronization, shared memory, source codes, and message queues, including source codes, it's a lot of stuff. I think it makes no sense for the final 3-4 minutes to start with pipes now, because so it's maybe for the trash bin. Let's have some minutes left for questions. And here we have the first question. I have a question: why do we use message queues when we can just create a file and processes can write and read from it? Actually, it's a good question. I think first answer I get pretty fast. If you stay in memory, it's a lot faster. If you go the way of file systems, you waste a lot more time. You can reduce this time today by using a RAM disk. Yeah, every modern Unix operating system has a RAM disk mounted in device shared memory, but it's still more overhead. Yeah, it's still slower. Yeah, message queues are just faster, I think. That's the best answer I have now. Another question: one student cannot register for the examination. Is it normal? You are an Erasmus student. Yeah. Reason is you did not participate algorithms and data structures at our university, but that's not your fault. You need to ask the examination office and they will register you. I have this question every semester sometimes, and so it's in the Q&A section of my course page, yeah, in the questions and answers section. You did not do something wrong. Yeah, just go to the or ask the examination office and they will register you. It's a special case, yeah, but it's not your fault. Some more questions, come on. Don't be shy. No more questions. Okay. So I think we 1 minute left. I think this 1 minute, single minute is our present. we use it in a useful way for whatever you want to do, but we will not waste it now. Okay, so see you in the exercise sessions. Good afternoon, yeah, you too, and have a nice day. See you. Another question. Well, I have another question. POSIX and System 5 are both shipped with the Unix kernel, right? The Linux kernel or all other Unix-like operating systems implement usually the System 5 system calls, and also the standard libraries implement functions for working with these System 5 system calls. POSIX is a library. It's just a standard it's a library implementation, and it's quite portable. Yeah, it's quite good portable. It has been ported to basically all modern operating systems. So it's just a different layer of the operating system. Yeah, System 5 is implemented by the kernel and POSIX by a library. Okay, so thank you for attending today, and see you soon. Bye bye.